Welcome to Sleepy Stories. In this episode, we will take a clear and steady look at the idea that space has no borders. The goal is to help you learn while you rest. If you do not fall asleep right away, that is completely fine. In the time you are awake, you will hear about the vast, borderless nature of space, from the structure of the universe to the way Earth appears from orbit. Simply listen, let your breathing slow, and allow the information to settle at its own pace. When we speak of space, we often imagine it as a place, a destination above, beyond, or outside. But space isn't a separate location. It's not a room with walls or a country with edges. It is the absence of boundaries, the continuous fabric in which everything exists. Space stretches in all directions, silently holding planets, stars, and galaxies. It has no signs, no fences, no customs to pass through. In its vastness, there are no passports, no ownership, and no roads. This lack of borders is not just poetic, it's physical. Unlike Earth, where nations define lines on land and water, space is shaped by forces, not by claims. There are no property markers between orbits, no zones carved into the void. The stars don't know where one country ends and another begins. From the perspective of the cosmos, Earth is a single, seamless body, moving through the dark with everything else. When astronauts orbit Earth, they often describe something profound: the complete absence of national boundaries. The planet appears whole, wrapped in thin clouds and blue oceans, marked only by geography, rivers, deserts, coastlines. Political borders, so meaningful from the ground, vanish entirely. The realization that these lines are invisible from space can be disorienting. It leads to what many describe as a psychological shift, a new perspective of unity, fragility, and shared responsibility. This story will move gradually through that idea that space has no borders. We'll begin with the shape of the universe itself, which may be infinite, curved, or expanding without a center. Then, we'll come closer to home, looking at how scientists define space using coordinates instead of countries. We'll visit the International Space Station, where people from many nations live and work together in a place without territorial division. We'll explore how spacecraft navigate without maps, how time shifts in orbit, and how even sleep changes when there's no gravity to guide the body down. Along the way, you'll hear about the real borders that do exist, the threshold of a black hole, the limits of the observable universe, and the edge of the solar system. But these are not borders of ownership. They are changes in state, points of transition, defined by energy, not politics. They mark the edges of influence, not of control. Even light travels without borders. The photons that strike your eyes may have begun their journey billions of years ago, passing untouched through clouds of gas, fields of gravity, and vast regions of space where nothing interrupted them. When we observe the cosmos, we are collecting messages that crossed no checkpoints, wore no labels. They simply traveled. The idea that space has no borders invites us to think differently, not only about space itself, but about how we define limits, control, and identity. It reminds us that many boundaries are temporary, local, and human-made. Space, by contrast, invites cooperation. It challenges division. It humbles us. It offers a canvas where what matters is not where you come from, but what you can discover. Tonight, let this story unfold slowly. There is no rush. The universe will not run out. It has no closing hour, no fence at the edge. Like space itself, this story will move in gentle curves, without corners, without hurry, and without boundaries. The idea of a universe without borders begins with a simple yet staggering question: does space have an edge? For much of history, humans imagined that the cosmos must have an outer limit, a place where the stars stopped and the void began. Ancient models proposed spheres, domes, and boundaries, structures that enclosed the universe like a giant shell. But as astronomy advanced, those edges fell away. Telescopes looked deeper, and no wall appeared. Measurements stretched farther, and still the universe continued. Today, scientists describe space not as a bounded container, but as a dynamic fabric, something that can stretch, curve, and expand. The observable universe is immense, more than 90 billion light-years across, but it is not the full story. That is only what we can see, limited by the time it takes light to reach us. Beyond that horizon, space may continue forever. One model suggests that the universe is flat, like an infinite sheet. In that case, it has no edge, just endless continuation. Another model proposes that the universe is closed, like the surface of a sphere. You could travel in a straight line forever and eventually return to your starting point, never crossing a border. Still, another possibility is that space is open, curving outward in every direction, expanding without bound. Each of these models fits current data, and each removes the need for a physical limit. But even in these models, the idea of a border becomes less useful. There is no outer wall to reach, no fence to pass. If the universe is infinite, it has no center, no perimeter, and no direction that leads to an end. If it is curved, it loops on itself. If it is expanding, that expansion is everywhere at once, not from a central point outward, but from every point away from every other. Every location sees itself as the center, because the expansion is not through space, it is of space. This concept is hard to picture, because human experience is based on boundaries. Rooms have walls, cities have edges, continents have coasts, but space, on the largest scale, defies that structure. It is not contained within anything. It does not sit inside a larger field. It is the field, and it is still growing. That expansion was first discovered in the 20th century, when astronomers noticed that distant galaxies were moving away from us, and not just from us, but from each other. The farther away a galaxy is, the faster it seems to recede. This pattern led to the idea of the Big Bang, not an explosion in space, but an expansion of space itself. Space stretches, and with it, the galaxies move apart. The universe has no outer edge where it meets something else. Instead, it is more like the surface of a balloon being inflated. Every point moves away from every other, and no single point is at the center. But unlike a balloon, space doesn't expand into anything. It creates more of itself. This challenges our sense of borders, because it shows us that some systems have none, not even in principle. In this story, as we move from one layer of space to the next, you may begin to sense how the universe resists boundaries, not only in theory, but in how it behaves. It does not respect our instinct to divide, contain, and label. It invites us to let go of those habits and instead observe what simply is. So if you're still awake, know that the idea of a borderless universe is not just philosophical, it is written into the structure of reality. And if sleep has begun to soften your focus, that's perfectly fine. The cosmos stretches on, with or without our attention. It welcomes your curiosity, your stillness, or your dreams, all equally. From the surface of Earth, borders seem absolute. We draw them on maps, carve them into laws, guard them with gates and signs. A single step across an imaginary line can mean a different language, a different currency, or a different set of rules. Borders organize life on the ground. They give shape to nations, responsibilities, identities. But from space, these lines vanish. When astronauts look down from orbit, they don't see fences or color-coded countries. They see coastlines, forests, rivers, deserts. They see vast swirls of cloud, the shimmering blues of ocean currents, and the golden glow of city lights. The only lines that appear are natural mountain ridges, tectonic fault zones, the winding paths of rivers. Even those blur with distance. The political lines that seem permanent from the ground dissolve under the lens of altitude. This is not just a poetic observation, it is a physical fact. Borders are constructs, not physical features. We use them to organize ourselves, to define regions of governance and protection. But they are not drawn into the Earth's crust. They are not etched into the sky. From above, the Earth is a single, continuous surface, dynamic, beautiful, and shared. The first people to see Earth from space reported a profound shift in perspective. They expected awe. What surprised them was the sense of unity. The planet looked whole, fragile, alive, and the absence of visible borders made the divisions between nations seem temporary and small. Some described it as a moment of deep clarity, where all the conflicts and divisions of the surface lost their grip, replaced by a vision of interconnection. This shift in awareness is sometimes called the overview effect. It doesn't come from theory, but from sight. When humans look down from space, they often report an emotional response, an instinctive understanding that the planet is one system, one biosphere, one home. Of course, on the surface, borders remain deeply relevant. They shape economies, laws, security, and cooperation. But the view from space reminds us that these borders are agreements, not absolutes. They can change, they have changed, and they exist within a larger, borderless context, the planet itself. Even phenomena that cross these artificial lines every day ignore them entirely. Weather systems roll across continents, unfazed by jurisdiction. Migrating birds follow paths older than civilization. Ocean currents move heat from the equator to the poles, influencing rainfall, wind, and climate without regard for national boundaries. Sometimes, satellites detect plumes of dust traveling from the Sahara Desert all the way to the Amazon rainforest, one continent nourishing another with minerals carried across an ocean. Aurora borealis ripples through the upper atmosphere, painting light across magnetic fields, not political maps. From the top of the atmosphere to the depths of the sea, Earth behaves as one unit. In this segment, we're not rejecting the need for borders, but we are placing them in perspective. The natural world flows across them. The planet's systems do not recognize them. And when seen from the altitude of space, they are gone entirely. So as your body settles and your breathing softens, let yourself float above that web of lines. Let them dissolve into the larger surface of Earth, cloud-covered, sunlit, turning slowly in the dark. In the silence of orbit, there is only connection, motion, and the living texture of a borderless world. If space has no borders, how do we find our way through it? Without roads, signs, or national zones, how do astronomers locate a star, or engineers guide a spacecraft? The answer is coordinates, not of countries, but of geometry and light. On Earth, we use latitude and longitude to specify locations. These are angles based on the equator and the prime meridian, projected across the globe. They're not physical features, but conceptual tools. In space, we use a similar system, celestial coordinates. These do not rely on borders or cities. They are defined by the rotation of Earth and the positions of stars. The most common system uses right ascension and declination. Right ascension is like longitude, but projected onto the sky. Declination is like latitude, marking how far above or below the celestial equator an object lies. Together, they allow astronomers to point their telescopes with precision to locate a galaxy, a pulsar, or a comet billions of kilometers away. These numbers form a universal grid. They apply equally from a desert observatory in Chile to a telescope on the moon. No country owns right ascension 12 hours, declination plus 45 degrees. These are positions on an imaginary sphere that surrounds Earth, a shared map of the sky with no zones, no borders, and no ownership. This approach is not limited to the sky. Spacecraft navigation also avoids borders. Trajectories are calculated using gravity, timing, and inertial reference frames. A probe leaving Earth uses Earth's motion, the Moon's pull, and the gravity of planets to swing itself outward. These calculations rely not on who controls which space, but on universal constants: mass, velocity, acceleration. The universe operates on principles, not politics. Its structure is mathematical. The location of a planet is determined by its orbit, not its jurisdiction. The path of a satellite depends on physics, not permissions. Even the International Space Station, though built through international collaboration, orbits Earth every 90 minutes, passing over dozens of countries without crossing a single meaningful boundary. To operate in space, cooperation becomes necessity. Shared data, synchronized clocks, common systems of measurement, these are required not by diplomacy alone, but by the nature of space itself. There is no space traffic control dividing orbits into nations. Instead, there are agreements, models, and mutual responsibilities. There's something deeply calming about this. In a world full of contested zones and competing claims, it is reassuring to know that space, by its very nature, resists division. Its order emerges not from law, but from reality. The sky is not owned. It is mapped, measured, and shared. This isn't to say space is free from human interest or ambition. Commercial satellites occupy specific orbital slots. Space agencies negotiate launch windows. But all of this still operates within a structure that no one can alter. The stars don't shift for preference. The vacuum makes no exceptions. The rules remain. So as you lie quietly now, perhaps beginning to drift, imagine this grid of the sky. Not a net to trap things, but a guide to help us move. A gentle framework across the stars, allowing us to find our place among them. Numbers, angles, and directions, clear, silent, borderless. You do not need to remember the terms. You do not need to calculate the coordinates. Just know that somewhere above you there is a map written in light, not law. And on that map, no one is excluded. Imagine watching the Earth from above. You're aboard a spacecraft, orbiting at over 27,000 kilometers per hour, circling the planet every 90 minutes. Beneath you, continents glide by, oceans, forests, mountain ranges, and cities lit like constellations at night. But as you look, something is missing. There are no borders. From orbit, political boundaries, so crucial on maps, disappear. The lines that define countries, divide people, and shape history are invisible from space. What remains are the features of nature: river deltas, deserts, storm systems, and coastlines. The Earth appears as one surface, interconnected and whole. This is more than an aesthetic observation. It is a reality experienced daily by astronauts. The absence of visible borders creates a powerful shift in perspective. Conflicts that seem vast on Earth shrink to the size of a shadow. Divisions fade. What becomes clear is the fragility of the atmosphere, the thinness of the layer that protects all life, and the shared patterns of land and water that sustain us all. This visual unity has consequences. It's one reason why space exploration, despite political tensions, has often fostered cooperation. The International Space Station is a striking example. Built and maintained by multiple nations, including the United States, Russia, Japan, Canada, and the European Space Agency. The station is a model of collaboration in an environment where survival depends on trust, precision, and mutual reliance. On board, astronauts of different languages and backgrounds work side by side. They share meals, experiments, tools, and stories. National identity doesn't vanish. but it recedes, becoming secondary to the shared mission of maintaining life and advancing science in a borderless environment. Even in lower Earth orbit, satellites cross over national territories in minutes. The Earth rotates beneath them, and orbits are determined by altitude and inclination, not sovereignty. A weather satellite might pass over half a dozen countries in one orbit, gathering data that helps predict storms, guide planes, or support agriculture, regardless of political divisions below. Treaties support this freedom. The 1967 Outer Space Treaty, signed by over 100 nations, affirms that outer space is not subject to national appropriation. No country can claim the moon or any other celestial body. While newer questions have arisen about resource extraction and private missions, the core idea remains: space is a global commons. Of course, tensions do reach into orbit. Nations test anti-satellite weapons, military satellites operate silently, and the question of who controls orbital traffic is becoming more complex. But despite this, space still stands apart as a domain where cooperation continues in ways that seem harder on the ground. There is something essential in this arrangement. Space demands cooperation. The vacuum does not allow for error. Microgravity and radiation do not bend to politics. In such an environment, isolation is risk, and division is weakness. Survival, exploration, and progress require working together. So as you settle now, perhaps beginning to relax more deeply, imagine yourself looking out a window at the Earth, not as a patchwork of countries, but as a single, turning sphere. The clouds do not stop at borders, the ocean does not ask for documents, the stars above shine on every surface equally. From this distance, the planet becomes what it always was: one place, and in the silence of orbit, the absence of borders becomes not just visible, but natural. In the stillness of orbit, where Earth's atmosphere falls away into darkness, and the pull of gravity gives way to weightlessness, even sleep begins to change. On Earth, gravity gives structure to sleep. We lie down, feel the pull of our body against the bed, and rest our head upon a pillow. Down is obvious, stillness is simple. But in microgravity, sleep is not bound by direction. There is no up, no down. Astronauts float. And in that floating, the body begins to learn something new: how to sleep without weight. Inside the International Space Station, crew members attach themselves to the walls in small, enclosed sleeping quarters. They use soft restraints or sleeping bags to prevent themselves from drifting through the air. The room doesn't have a floor or ceiling. The astronaut can choose any orientation: head up, feet up, sideways, and it makes no difference. The environment does not impose a direction. The space station orbits Earth once every 90 minutes. That means 16 sunrises and 16 sunsets in every 24-hour period. The absence of a true day-night cycle challenges the body's circadian rhythm. Without cues from sunlight and darkness, the brain can lose its sense of time. To counter this, astronauts follow strict schedules. Lights are programmed to mimic Earth's day. Work periods, meals, and rest are timed precisely to support internal regulation. Still, many report difficulties sleeping. In the early days of a mission, it can be hard to adjust. The constant background hum of fans and equipment, the presence of carbon dioxide pockets near the face, and the slight but persistent awareness of floating can keep the mind alert. Some astronauts describe waking frequently or having lighter, more fragmented sleep, but others report a different experience, one of deep peace. With no pressure points on the body, no weight bearing down, and no tossing or turning, the body can release its usual tensions. The sensation of suspension can be calming, like floating in warm water. There are no sheets to tangle in, no mattress to press into the spine, just a body held in place by its own inertia, cradled by silence and darkness. And it is very dark. Outside the station's thin walls lies the vacuum of space, a blackness so complete that it becomes not just visual, but emotional. There are no city lights, no passing cars, no sounds from the outside world, only the occasional reflection of Earth, the faint twinkling of distant stars, and the constant, slow movement of orbit. This quiet is not emptiness. It is a kind of fullness, the presence of everything that exists beyond noise. For those lying in their sleep quarters, this background becomes part of the rhythm of rest, a reminder that even here, surrounded by technology and movement, there is stillness. Back on Earth, your own sleep may not feel like zero gravity, but in its own way, it is a release from weight. The body becomes heavier as it prepares to rest. Muscles soften, thoughts loosen, and eventually, awareness slips away. You enter a space without edges, without borders, one shaped not by geography, but by dreams. If you're still awake, you might imagine what it would be like to float freely in a quiet chamber, with no direction, no motion, and no demands. The breathing slows, the heartbeat softens. There is no need to resist the stillness. Let it hold you. Sleep, like space, offers a version of weightlessness, not of the body, but of the mind, a place where gravity's concerns no longer pull so hard. And as the earth turns far below, and the stars continue their quiet burn, your own stillness begins to deepen. Here, in the borderless dark, sleep can finally begin. Where does space begin? It seems like such a simple question. But the answer, like much of what we've explored, resists a precise boundary. There is no wall, no invisible dome, no sharp transition from the blue skies of Earth to the blackness of space. Instead, there is a gradient, a slow, graceful thinning of the air, a dissolving of pressure, molecules, and motion. The edge of space is not a line, it is a change. Atmospheric layers give us structure, each with its own name, properties, and behavior. The troposphere hugs the ground, the lowest layer where weather happens and clouds form. Above that lies the stratosphere, home to the ozone layer. Then comes the mesosphere, followed by the thermosphere, and finally the exosphere, the outermost region, where particles drift off into space. Each layer becomes thinner than the last, until the density of molecules is so low that they no longer behave like a gas. And still, the question remains, at what point does the atmosphere end and space begin? Internationally, the most widely recognized definition is the Kármán line, named after aerospace pioneer Theodor von Kármán. It lies at an altitude of 100 kilometers, or about 62 miles, above sea level. At this height, the atmosphere is so thin that aerodynamic flight becomes impossible. Wings no longer generate lift. To stay aloft, an object must move so fast that it essentially falls around the Earth, achieving orbital velocity. This is not a legal threshold, but a practical one, based on physics rather than politics. But other definitions exist. Some agencies place the boundary at 80 kilometers. Others view it as a continuous decline rather than a fixed point. After all, air molecules don't stop at the Kármán line. They continue to exist far above it, drifting in the exosphere, influenced by solar winds and magnetic fields. Satellites in low Earth orbit, such as the International Space Station, still experience trace atmospheric drag, requiring regular altitude boosts to stay in place. The absence of a sharp edge reminds us of something deeper, that nature prefers gradients over walls. Even the word edge is a convenience, a way to describe a boundary that is useful for planning, but not necessarily real in a physical sense. The transition from atmosphere to space is like the fading of twilight into night. There is no single moment when the sky turns black. Instead, light scatters less and less, stars begin to emerge, and the sense of openness expands. In the same way, As altitude increases, the sky deepens from blue to indigo, and then to black, not because something changes suddenly, but because molecules grow scarce, scattering stops, and the sunlight travels uninterrupted. This segment is a reflection on that quiet threshold. It invites a sense of humility. Our atmosphere, while vital and complex, is fragile, a thin veil wrapped around a rocky sphere. It protects us, nourishes us, shields us from harmful radiation, and gives us air to breathe. But it ends, softly, somewhere not so far above our heads. From a cosmic perspective, it is astonishing how little separates us from space. If you were to rise through those layers, through the troposphere's turbulent clouds, into the calm of the stratosphere, beyond the glow of auroras in the thermosphere, you would feel no sudden change. There would be no sound, no warning, no threshold crossed with certainty, only the subtle signs. The sky darkens, the air no longer presses against you, and the curvature of Earth becomes visible below. In time, you would find yourself not on Earth, but above it. This transition is not a boundary in the traditional sense. It is a shift in conditions, a movement from one domain of physics into another, from weather to radiation, from lift to orbital velocity, from breath to vacuum. And so, the edge of space is not a place, but a process. On Earth, up and down feel absolute. Gravity pulls everything toward the center of the planet, giving direction to every motion and shape. Trees grow upward, water flows downward. We stand on floors, climb stairs, fall, rise, kneel, lie down. Our entire experience of space is shaped by that single force, anchoring everything to a consistent vertical reality. But in orbit, that structure dissolves. In the microgravity environment of space, objects no longer fall, they float. A wrench let go in the International Space Station simply stays where it is, drifting gently and less moved. An astronaut pushing off from one wall won't fall. They'll glide across the module, slowly, until stopped by another surface or handhold. And with the disappearance of gravity's pull, the concept of up and down becomes meaningless. There is no floor, there is no ceiling, there is no correct orientation. Astronauts quickly learn to let go of terrestrial instincts. They sleep in vertical or horizontal positions. They eat while upside down. They move through modules with their feet above their heads, and it feels normal. The station itself reflects this freedom. Inside, there is no fixed top or bottom. Equipment is installed on all surfaces. Labels on walls may face different directions, depending on which way you choose to view them. Each crew member orients themselves based on function, not physics. What matters is where a tool is, not which way gravity would have pulled it. This shift in perspective is more than physical. It's neurological. On Earth, the brain uses input from the vestibular system in the inner ear to determine balance and orientation. Tiny fluid-filled canals detect motion and help us stay upright. In microgravity, that system no longer functions the same way. The signals become unreliable. At first, many astronauts experience space adaptation syndrome, a temporary form of motion sickness. But the brain adjusts. Within a few days, it rewires its expectations. Without gravity, the sense of up and down simply fades. Children often imagine floating through space as magical, and in some ways, they're right. But it's also a challenge. On Earth, we rely on gravity to help with digestion, blood circulation, and even basic movements like walking or lifting. In orbit, these processes must be relearned. The body must find new reference points. Moving from one place to another becomes a matter of gentle pushes, gliding, and grabbing rails. Every motion is deliberate, every orientation is optional. Yet for many astronauts, the experience becomes freeing. Without gravity assigning direction, movement becomes graceful. effort becomes minimal. The mind lets go of the need to define position. In the absence of gravity, many report a sense of flow, a quiet freedom, where the body can rotate, drift, and settle wherever it needs to, without strain or force. Outside the station, the effect is even more profound. During spacewalks, astronauts are surrounded by infinite darkness. The Earth may lie beneath their feet or above their heads. The sun could rise from any direction. There is no sky. There is only distance, light, and movement. Orientation becomes a choice. And in that choice lies a powerful shift, not only in how we move, but in how we perceive ourselves. Back on Earth, we often think in vertical terms. Higher is better, falling is failure, climbing is achievement. But in space, there is no hierarchy of direction, no top, no bottom, just movement, balance, and position relative to other things. This absence of verticality is not disorienting forever. It becomes a new normal. The body adapts, the mind adjusts. And in that adjustment, a deeper insight emerges that the way we define space is shaped not by nature, but by context. Space, in its purest form, offers no directions. It simply is. Space is often imagined as empty, silent, and still. And in many ways, that's true. But its silence is not the silence of a quiet room. It is more complete than that, more absolute. It is the silence of a vacuum, a place where sound cannot exist because there is no air to carry it. On Earth, every sound we hear is created by vibrations in a medium. A voice moves air molecules. A bell causes metal to oscillate, which pushes against the air, sending waves toward our ears. Even the crunch of leaves or the crack of thunder depends on the presence of matter. In space, that medium is missing. The molecules are so sparse, sometimes just a few per cubic centimeter, that vibrations have nothing to travel through, no medium, no sound. If you were to float outside a spacecraft, you would see a world in motion, rotating planets, expanding gas clouds, flickering stars, and burning suns. But none of it would make a sound. Even if two asteroids collided with explosive force, their impact would be completely silent unless you were physically connected to them. There would be no crash, no bang, no roar, only motion and light. This silence is not a lack of activity. It is simply a lack of air. Space is full of motion and interaction, just not in ways our ears can detect. Radiation streams through the cosmos. Solar flares erupt from stars. Entire galaxies collide in slow-motion ballets that span millions of years. Black holes twist the fabric of space-time itself. But all of this unfolds in a quiet that is total. Instead of sound, space is filled with electromagnetic waves. These are forms of energy that do not require a medium. Light, X-rays, radio waves, gamma rays, they all move effortlessly through the vacuum. Our instruments can detect them, convert them into data, and sometimes even translate them into sounds we can hear. But this translation is artificial. The waves themselves are not sound. They are invisible patterns of energy, gliding silently through the void. Astronomers have learned to listen to the universe using telescopes that pick up these waves. Radio telescopes detect signals from distant pulsars. Infrared sensors track the heat of newborn stars. Gamma-ray detectors catch the echoes of supernovae. None of these produce a sound in space, but they reveal an orchestra of activity that plays continuously, silently, everywhere. For astronauts, the silence of space is not just external, it becomes internal. Once outside a spacecraft on a spacewalk, there is no ambient sound. The only things they can hear are transmitted through their suits: the hiss of airflow, the hum of electronics, their own breathing, and the occasional voice from mission control. Some describe it as eerie. Others describe it as peaceful. Either way, the silence makes every movement feel more deliberate. It enhances awareness. It deepens presence. This silence also has a psychological effect. On Earth, we are surrounded by constant noise, machines, conversations, traffic, wind. Our brains learn to filter and interpret these layers. But, in space, stripped of those sounds, the mind becomes more attuned to its own rhythms. Some astronauts report a heightened sense of calm. Others feel disoriented, as though their senses are searching for something that isn't there. But the quiet of the void is not absence, it is clarity. In the stillness, every flicker of light matters more. Every movement carries intention. The background hum of earthly life is replaced by the raw mechanics of existence. Orbit, inertia, mass, and momentum. And yet, for all its silence, space is not empty. It contains the dust of ancient stars, the frozen breath of comets, the echoes of the Big Bang. Particles race at near light speed. Fields of energy weave invisible structures through galaxies. Dark matter shapes the motions of stars we cannot see. Even in the vastest regions, something is always happening. It just doesn't speak in the ways we are used to. To exist in space is to exist in a world of motion without sound, energy without voice. It is to witness forces beyond hearing, and in that quiet there is a strange kind of truth, one that doesn't need to be spoken to be known. Orbiting roughly 400 kilometers above Earth, the International Space Station, known as the ISS, is one of the most remarkable achievements of human cooperation. It moves silently through space at over 27,000 kilometers per hour, circling the planet every 90 minutes. At first glance, it appears to be a machine: solar panels, modules, metal beams, and antennas. But inside, it is something more human: a laboratory, a workplace, and most of all, a shared home without borders. The ISS is not owned by one country. It is the result of collaboration among multiple space agencies, including NASA, United States, Roscosmos, Russia, ESA, Europe, JAXA, Japan, and CSA, Canada. These agencies have different languages, funding systems, engineering traditions, and histories, yet they came together to build something that no single nation could achieve alone. Construction of the station began in 1998, when Russian and American modules were launched and docked in orbit. Over the next 2 decades, additional modules, laboratories, living quarters, and solar arrays were added, creating a football field-sized structure that now hosts up to 7 crew members at a time. The modules themselves reflect their origins, each built in different countries, launched by different rockets, and designed to perform different functions. But in orbit, they are seamlessly connected, forming one functional whole. Inside the station, crew members from different nations live and work together. They conduct scientific experiments, monitor Earth's climate, test the effects of microgravity on the human body, and maintain the complex systems that keep them alive in an environment utterly hostile to human life. They share meals, celebrate holidays, and support each other during long missions far from home. The ISS operates on Universal Coordinated Time, UTC. Daily routines are scheduled across time zones and cultural backgrounds. Communication with ground stations takes place in multiple languages. All crew members, regardless of nationality, receive extensive training in each other's systems. An American astronaut must be able to operate Russian modules. A European scientist may need to use a Japanese experiment rack. Every person aboard becomes, in some sense, a citizen of space. This shared space is not just metaphorical, it is physical. There are no walls between modules, no visa checkpoints, no ownership signs. Air flows freely from one compartment to the next. Power is distributed across solar arrays, regardless of who built them. Water is recycled and reused by everyone aboard. And when something breaks, it is repaired not by the nation who launched it, but by the hands that are there. The absence of borders on the ISS is not accidental. It is the product of necessity. In orbit, survival depends on collaboration. Space does not forgive division. A malfunction in one module can affect the entire station. Supplies arrive on cargo ships from many countries, each carrying vital equipment, food, and oxygen. Politics may shape policy on Earth, but in orbit, functionality and trust take precedence. This cooperation extends beyond logistics. The ISS has been a platform for diplomacy even during times of tension on the ground. American and Russian astronauts have continued to work side by side through geopolitical friction. The mutual dependence required to operate the station often outlasts fluctuations in international relations. But the ISS is not just a symbol of peace, it is a working laboratory. More than 3,000 experiments have been conducted there, spanning biology, physics, medicine, materials, science, and Earth observation. Microgravity offers unique conditions for studying phenomena that behave differently without the constant pull of gravity. Proteins crystallize more purely, fluids mix in unfamiliar ways. Human physiology adapts, weakens, compensates, and teaches us about health on Earth and the future of long-duration missions. In this way, the station is more than a home. It is a bridge between nations, between science and experience, between what we know and what we are learning. It orbits above a world full of boundaries, but carries none itself. As it passes silently overhead, the ISS reminds us of something both simple and profound, that borders are choices, and sometimes, when the stakes are high enough and the vision is wide enough, we can choose not to draw them. The universe, for all its vastness, is not a random scattering of stars and galaxies. It is structured, woven together by gravity into vast cosmic neighborhoods. These neighborhoods are not defined by flags, territories, or jurisdictions, but by natural relationships: motion, mass, proximity, and attraction. They are shaped by the invisible pull of gravity, stretching across millions of light years, forming patterns far larger than any one galaxy. Our own neighborhood begins with the solar system. At its center is the Sun, a medium-sized star orbited by 8 planets, dozens of moons, countless asteroids, and vast fields of icy bodies in the Kuiper Belt and beyond. Everything in this system is held together by the Sun's gravity. It is the anchor of our local space, binding us in a silent, continuous orbit. But the solar system is just a small member of the Milky Way galaxy, a vast spiral of stars, gas, and dark matter. The Milky Way contains more than 100 billion stars, each potentially accompanied by its own system of planets. These stars orbit the galaxy's center, a densely packed region that likely hides a supermassive black hole. Our solar system, located in a relatively quiet arm of the galaxy, takes about 230 million years to complete one rotation around the galactic core. The Milky Way itself is not isolated. It is part of a collection of galaxies known as the Local Group. This group includes more than 50 galaxies, most of them small dwarf galaxies, along with 2 large spirals, the Milky Way and the Andromeda Galaxy. These 2 giants are gravitationally bound to each other and are slowly moving closer. In about 4 billion years, they will merge in a cosmic dance, forming a new galaxy with a shape yet unknown. Beyond the Local Group lies an even larger structure, the Virgo supercluster. This immense region of space contains thousands of galaxies grouped into clusters and filaments, connected by gravity but separated by vast stretches of intergalactic void. The Virgo supercluster is part of a still greater structure called Laniakea, meaning immense heaven in Hawaiian, a name chosen to reflect its scope and coherence. Laniakea includes the Virgo supercluster and many others, all flowing together in a gentle gravitational current toward a focal point known as the Great Attractor. None of these structures are marked by lines. There are no signs indicating where the local group ends and the Virgo supercluster begins. These borders are defined by behavior, how galaxies move relative to each other, how gravity influences their paths, how dark matter shapes their distribution. Scientists use redshift data, velocity measurements, and gravitational models to trace these relationships. The result is a map, not of possession, but of connection. What's remarkable about this map is how uncentered it is. Every part of it can be viewed as a center, depending on your frame of reference. The universe doesn't have a single core from which everything expands. Instead, it expands everywhere at once. Every galaxy, every cluster, every supercluster is part of the larger whole. There is no privileged position, no cosmic capital city. This view stands in contrast to how humans often organize space. On Earth, we define neighborhoods by fences, roads, and postal codes. We assign ownership and build walls. But the cosmos doesn't divide itself this way. It organizes by force, gravitational, electromagnetic, nuclear, and within those forces, matter gathers and flows, creating islands of complexity in a sea of darkness. The idea of cosmic neighborhoods helps us understand where we are, but it also reminds us of how connected everything is. The atoms in your body were forged in ancient stars within this galactic structure. The light we see from distant galaxies travels through these gravitational lanes, shaped by the curvature of space-time itself. So, as we move through this story, drifting gently across the scale of the universe, remember that space organizes not by division, but by relation. Galaxies are neighbors not because they are near in miles, but because they move together, evolve together, and shape each other. It's a quiet kind of community, one without walls, without names, and without borders. In the great silence of space, between the pulses of stars and the long arcs of galaxies, there is a kind of stillness that invites rest. Not the rest of motionless bodies or quiet rooms, but something deeper, a slowing of thought, a widening of perspective, a release from the noise of urgency, and perhaps, if conditions allow, a moment of sleep. Astronauts have described spacewalks as dreamlike. Floating outside the International Space Station, they are tethered only by a thin line of fabric and metal, drifting over the entire spinning world. No up, no down, just the vast blackness of space, scattered with points of light. The stars do not twinkle here, the atmosphere is gone. Each star appears steady, sharp, precise. The stillness is so complete, the body begins to soften against it. Breathing slows, awareness narrows. What remains is motion, breath, and a growing calm. For those of us on Earth, sleep is usually accompanied by gravity, walls, warmth, and familiar surroundings. But in this segment, we drift away from those anchors and instead imagine a kind of rest that resembles orbital suspension, a gentle float through starlight and dark, supported by nothing but space itself. Scientifically, sleep in space is both familiar and altered. The absence of gravity changes the way blood circulates, the way the spine stretches, and the way fluid shifts toward the head. Astronauts often report nasal congestion and puffy faces. Without the natural cues of sunrise and sunset, circadian rhythms can shift or fragment. Crew members use artificial lighting, carefully timed schedules, and melatonin to regulate their internal clocks. Even so, the body adapts. Sleep arrives, not always easily, but reliably. Inside the space station, sleep quarters are the size of small closets. They are soundproofed, darkened, and gently ventilated. A sleeping bag is tethered to a wall. A laptop might glow with messages from home, Personal items float in mesh pouches. There is no need for a bed, no need to lie down. In microgravity, the body hangs in equilibrium, limbs relaxed, joints uncompressed, floating in a posture that mimics deep relaxation. And here on Earth, even as we are held by gravity, we can share in that image. Sleep does not require walls to define it. It does not need a fixed surface beneath us. What it asks for is surrender, a letting go of effort, a loosening of the thoughts that try to stay awake. In this way, space and sleep resemble each other. Both begin with the quiet decision to stop resisting. If you are still awake now, it is perfectly fine. Sleep does not arrive on command. It comes when the conditions are ready, when the noise has softened, when the temperature is gentle, when the thoughts have cooled into a slower rhythm. The body begins to fall inward, as if becoming lighter, not floating, perhaps, but releasing its need to stay upright. Imagine yourself drifting, not in a bed, but in a chamber of still air, like the inside of a spacecraft. There is no weight. Your arms rest where they are. Your spine uncoils. There are no edges, no pillows, no pressure points, just breathing, soft and even, and the distant sense of stars around you. Outside, the Earth turns. The station moves in silence. On board, another orbit begins. The sun rises again, not with heat, but with light. But here, within the shelter of calm, time stretches. Sleep becomes its own kind of journey. There is no need to chase it. There is only the stillness to welcome it. If your eyes are closed now, let them stay that way. If your breathing has slowed, let it deepen. You do not need to hold on to this story. It will continue, quietly, whether you hear the next part or not. Like a star's light crossing space, it will keep moving, and if you fall asleep along the way, that too is part of the journey. Across every corner of the observable universe, from the smallest atom to the largest galactic cluster, one thing remains consistent. The laws of physics apply everywhere. They do not change from one country to the next. They do not adjust for language, belief, or boundary. They are not local customs. They are not artifacts of culture. They are the shared foundation of reality, unchanging, borderless, and universal. Consider gravity. The same force that holds your feet to the ground also governs the orbit of the moon, the curve of Saturn's rings, and the dance of galaxies. It was gravity that allowed stars to form in the first place, pulling together hydrogen atoms until pressure and heat ignited nuclear fusion. It is gravity that causes time to slow near a black hole, and that gives planets their seasons, tides, and orbits. Then there is light. The speed of light is a constant throughout the universe. It travels at exactly 299,792,458 meters per second in a vacuum. No matter the star, the direction, or the observer, this speed remains the same. This single rule anchors many others. It shapes our understanding of time, distance, and causality. It defines the very fabric of space-time in Einstein's theory of relativity. These laws are not just consistent, they are predictive. They allow us to describe how particles interact, how planets move, how radiation behaves, and how matter responds to force. We use them to build rockets, design telescopes, and understand the birth of stars. Whether in a laboratory on Earth or in the cold void between galaxies, these principles remain unchanged. They are also elegant in their symmetry. Electromagnetism, for instance, binds atoms together, lights up the sky with auroras, powers the circuitry of computers, and drives the engines of stars. The same four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, govern everything from the spin of an electron to the collapse of supernovae. What's most profound is that these laws appear to hold even in places we cannot reach. When we observe distant galaxies, we find their stars emitting light just as ours do. Their rotation curves obey the same gravitational equations. Their behavior, though alien in scale, is familiar in rule. This gives science a powerful tool. It means that the universe is knowable, not because we control it, but because it operates consistently. It also connects us. The iron in your blood was formed in the heart of a star by nuclear fusion, governed by the same physics that operates today. The photons that strike your eyes originated in the sun, following quantum paths, governed by the same equations that drive photosynthesis in a leaf or the glow of a nebula. In space exploration, the universality of physics is essential. We calculate spacecraft trajectories using Newton's laws. We predict planetary motion with Kepler's rules. We guide probes across billions of kilometers using gravitational assists, trusting that mass and motion will behave as expected, even at the edge of the solar system. The borderless nature of physics extends even to thought. A mathematical equation written in China is understood in Chile. A discovery in a lab in France can be confirmed by researchers in Canada or South Korea. The symbols may vary slightly, but the relationships remain the same. This common language is one of the most powerful, unifying tools humanity possesses. In a universe where distance often separates and differences abound, physics offers something profound: sameness. The same rules apply to all. There is no cosmic favoritism, no exemptions, no geopolitical distortion of mass, force, or time. And in that sameness, there is beauty. Order arises not from command, but from law. Motion follows patterns, not imposed by hand, but revealed by logic. In the dance of galaxies, in the flicker of particles, in the shaping of light, we see the same instructions playing out over and over again. These are not just facts. They are invitations to understanding. They remind us that no matter how far we travel, no matter how different the worlds we discover may appear, the rules will already be there, waiting to be uncovered, never needing translation. Space, for all its vast and silent beauty, is not empty. Between the planets, beyond the rings of Saturn and the orbits of satellites, there is movement, fast, constant, and sometimes dangerous. Small pieces of matter drift through the solar system at immense speeds. They are called micrometeoroids, and although many are no larger than grains of sand, they carry enough energy to pierce metal. A micrometeoroid is typically a fragment of rock, dust, or metal shed from a comet, asteroid, or even a planetary collision. These particles are ancient, some formed in the early solar system, others born from more recent impacts. They are not directed, organized, or owned. They travel along paths set by past forces, shaped by gravitational tides, solar radiation, and momentum, and they do not care what lies in their path. In the vacuum of space, there's no friction to slow them down. A micrometeoroid might travel at tens of kilometers per second, faster than any bullet fired on Earth. At those speeds, even something as small as a paint chip can cause serious damage. A direct hit on a spacecraft, if unshielded, could puncture a fuel tank, crack a window, or tear through insulation. Satellites, space stations, and spacecraft are designed with this in mind. Their hulls are reinforced with special materials. The Whipple shield, for example, is a multi-layered barrier that protects against micrometeoroid impacts. The first layer breaks the incoming particle into smaller fragments. The second and third layers then absorb the distributed energy. It's an elegant defense against a chaotic threat. Still, the danger is not theoretical. The International Space Station regularly encounters small impacts. Tiny pits and craters have been found on solar panels, windows, and handrails. In most cases, the damage is cosmetic or easily repaired, but occasionally, Larger debris must be tracked and avoided altogether. Ground-based radar systems scan the skies for orbiting junk, pieces of old rockets, decommissioned satellites, and fragments from previous collisions. Micrometeoroids, unlike larger space debris, are much harder to detect and track. They are too small, too fast, and too numerous. Every day, Earth is bombarded by more than 100 tons of dust and rock. Most of it burns up in the atmosphere, becoming meteors, streaks of light we call shooting stars. But in orbit, there is no protective atmosphere. Every particle is a potential threat. Astronauts are trained to respond to micrometeoroid events. The station can be maneuvered to avoid tracked debris. Emergency protocols exist for cabin depressurization. Spacesuits, used for extravehicular activities, include hardened visors and layered fabrics to resist puncture. Yet there remains a certain vulnerability, an acceptance that not everything can be controlled. This is one of the paradoxes of space. In its openness, it carries invisible risks. There are no borders in space to keep threats out, no fences to mark safe zones. The vacuum does not distinguish between science missions and spare parts. Everything moves together in an intricate and sometimes hazardous ballet. Micrometeoroids remind us that the absence of borders is not always peaceful. Sometimes it means exposure. It means accepting risk from every direction. It means designing for unpredictability and preparing for what cannot be seen. But it also encourages humility. Earth's atmosphere shields us from most of this debris, burning it up before it reaches the surface. We live beneath a dome that filters danger daily. The sky, often viewed for its beauty, is also a layer of protection, a thin, invisible shield that keeps countless impacts at bay. Above that shield, in low Earth orbit and beyond, we face space as it is, unfiltered, wild, and indifferent. And yet we persist, we build, we launch, we explore, not because space is safe, but because it is worth reaching. There are no territories to hide behind, no designated safe corridors, but there is knowledge, engineering, and the shared effort to make space more navigable. To survive in a borderless environment, we rely not on exclusion, but on foresight, preparation, and cooperation. When we look up into the night sky, it's easy to feel small. The stars seem impossibly far, the distance is overwhelming, the scale beyond comprehension. And yet, science has found ways to measure even the seemingly immeasurable. Light becomes a ruler, motion becomes a clock, and space, for all its vastness, begins to take shape, not through borders or boundaries, but through relationships and tools designed to reach across emptiness. On Earth, we measure distance in meters, kilometers, or miles, units based on tangible movement and geometry. But in space, these units quickly become inadequate. The Moon is nearly 400,000 kilometers away. The Sun is 150 million. The next nearest star system, Alpha Centauri, lies more than 4 light-years from us, so distant that even the fastest spacecraft built today would take tens of thousands of years to reach it. To describe such scales, astronomers use light-years, the distance light travels in 1 Earth year, nearly 9.5 trillion kilometers. It's not just a unit of distance, but a measure of time. When you look at a star that's 100 light-years away, you're seeing it as it was a century ago. The light arriving at your eyes tonight began its journey long before you were born. In this way, space becomes not just vast, but layered in time. We also use parsecs, a unit based on parallax, a method of measuring distance by observing how a star appears to shift against the background of more distant stars as Earth orbits the Sun. This geometric technique allows astronomers to triangulate the position of nearby stars with astonishing precision. It works only for relatively close objects, but it laid the foundation for a deeper map of the cosmos. For more distant galaxies, scientists use redshift, the stretching of light to longer, redder wavelengths as objects move away from us. It's a cosmic Doppler effect, and it reveals how fast a galaxy is receding due to the expansion of the universe. The greater the redshift, the farther the galaxy. By measuring redshift, we can infer distances to objects billions of light years away, beyond anything we could ever travel to, but not beyond our ability to study. And all of this is done without ever touching the objects in question. No one has been to Alpha Centauri, no spacecraft has visited the Andromeda Galaxy, and yet we know their distance, motion, composition, and structure. We measure what we cannot reach by interpreting the light that crosses space, by comparing angles so small they require space-based observatories, by trusting in the laws of physics to hold across unimaginable scales. These methods are not guesswork. They are carefully calibrated, tested, and verified. Astronomers use standard candles, such as Cepheid variable stars, to calculate distances, because their intrinsic brightness is known. By comparing how bright they appear to how bright they actually are, we can determine how far away they must be. Type Ia supernovae serve a similar role, offering consistent luminosity across vast distances. All of these tools show that space, while borderless, is not unknowable. We cannot mark its limits, but we can chart its depths. We cannot enclose it, but we can understand it. Its structure is not drawn in lines, but in patterns of light and energy. There is something profound in this approach. Instead of relying on contact or containment, we rely on interpretation. Space is measured not by what we can hold, but by what we can observe and calculate. In this sense, astronomy becomes an art of listening, of hearing what space tells us through the signals it sends. And though space continues beyond our reach, it does not withhold itself. It offers clues, shadows, pulses, and arcs. It offers consistency. It offers rhythm. We may never touch a quasar or cross a galaxy, but we can know them. We can draw maps not of ownership, but of presence. In a world where so much depends on possession, on knowing what belongs to whom, space invites a different kind of measurement, one that is quiet, persistent, and shared, one that sees value not in claiming, but in knowing. For most of human history, land has been claimed, fenced, named, defended. Ownership has defined the shape of civilizations, the rise of nations, and the conflicts between them. But when it comes to space, this open, vast, borderless expanse, the old rules do not fit. There are no farms to till, no cities to build, no gates to close. And yet, the question lingers: who owns space? Legally, the foundation of space ownership, or rather, the lack of it, begins with the Outer Space Treaty, signed in 1967 by the United States, the Soviet Union, and the United Kingdom, and now ratified by over 100 nations. This document states that outer space, including the Moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. In other words, no country can own space. The Moon cannot be colonized as territory. Mars cannot be planted with a flag and claimed as an extension of a government. Space, according to the treaty, is the province of all mankind, a domain to be explored and used for the benefit of all, not a new realm to be divided. This approach was visionary, anticipating the rapid expansion of space technology and the potential for conflict. It enshrined principles of peace, cooperation, and scientific openness. Military installations are banned from celestial bodies. Nuclear weapons are prohibited in orbit. The treaty urges transparency, mutual assistance, and shared responsibility. But, as technology evolves, so do the questions. Private companies now launch rockets, land payloads, and plan missions to the moon and beyond. Satellites provide internet coverage, Earth observation, and global communication, all managed by commercial enterprises. Space mining is on the horizon. Companies have proposed extracting water from asteroids, helium-3 from the moon, or precious metals from near-Earth objects. Can these materials be owned, even if the celestial bodies cannot? In response, some nations have passed laws attempting to clarify these rights. The United States, for example, passed the Commercial Space Launch Competitiveness Act in 2015, allowing American citizens to own resources extracted from space. Luxembourg and the United Arab Emirates have introduced similar legislation. These efforts argue that while space itself cannot be claimed, what is harvested from it may be. Much like fishing international waters or collecting minerals from the ocean floor, these legal frameworks are new, and their global acceptance is uncertain. Critics argue they violate the spirit of the Outer Space Treaty. Supporters claim they provide the legal clarity needed for innovation. In either case, the reality is this: space is no longer the exclusive realm of governments. It is becoming a domain of shared use, commercial interest, and complex legal evolution. Ownership in space is also about orbits. Geostationary satellites, for example, are positioned over specific points on Earth. Their orbital slots are limited, and they must be coordinated to avoid collisions and signal interference. These positions are managed by the International Telecommunication Union, which allocates frequencies and orbital locations. Again, no one owns the space itself, but the ability to use a part of it is regulated. There's also the question of responsibility. The Liability Convention of 1972 holds countries accountable for any damage caused by their space objects, even if operated by private companies. If a satellite crashes into another or a piece of debris causes harm, the launching state is responsible. In this way, space law extends beyond ownership. It includes stewardship. Perhaps this is the most important shift, from possession to responsibility. In a place where no one owns the land, what matters is how that space is used, protected, and shared. Ownership becomes less about control and more about care. As more missions are launched and more actors enter space, the need for international coordination grows. Space law is not fixed, it's still unfolding. It must balance freedom and fairness, innovation and ethics, ambition and caution. Space is not a blank slate, nor a lawless frontier. It is a shared realm, open, fragile, and filled with potential. What we do with it will shape not only exploration, but the very idea of what it means to own something beyond Earth. The solar system feels familiar, anchored by the sun, organized by planets, structured by orbits we've memorized since childhood. Mercury closest, Neptune farthest. But where, exactly, does it end? What lies beyond Neptune's cold path? Is there a clear boundary between what belongs to our star and what doesn't? Like much in space, the answer is layered. The solar system does not have a sharp edge. Instead, it has zones, shells, and gradients, regions defined not by lines, but by influence. The farther you go, the more the sun's grip loosens, until eventually, space belongs more to the galaxy than to our system. The most widely accepted boundary of the solar system is the heliopause, a distant frontier where the solar wind, a stream of charged particles emitted by the sun, is finally stopped by the interstellar medium. This is not a wall, but a threshold where pressures balance. On one side, the sun's particles dominate. On the other, the galaxy's environment takes over. The heliopause lies well beyond the outer planets, roughly 120 astronomical units AU from the Sun, 1 AU being the distance from Earth to the Sun, about 150 million kilometers. That places the heliopause at around 18 billion kilometers away. It is far beyond Pluto, in a realm of deep cold and quiet, where the sun is no longer a warm center, but just the brightest star in the sky. This region was crossed by Voyager 1" 2012 and Voyager 2" 2018. These two spacecraft, launched in the 1970 seconds, are now the farthest human-made objects from Earth. As they moved through the heliosphere, the bubble created by the solar wind, they eventually detected a sharp drop in solar particles and a rise in galactic cosmic rays, signaling their entry into interstellar space. But even this isn't the final boundary. Beyond the heliopause lies the Oort cloud, a theoretical shell of icy objects that may extend as far as 100,000 AU from the Sun, nearly halfway to the next nearest star. The Oort cloud has never been directly observed, but it is thought to be the source of long-period comets, those that take thousands or even millions of years to orbit the Sun. These icy bodies, barely bound by gravity, drift at the outermost edge of the Sun's domain. They represent the farthest reach of our solar system's gravitational influence. And yet, even this definition is not absolute. Gravity has no cutoff point. Its pull weakens with distance, but it never fully disappears. The Sun's gravity may stretch endlessly, becoming weaker and more diffuse, but still shaping the motions of distant objects in subtle ways. In this sense, the solar system doesn't end, it fades. It transitions from a zone of control to a zone of influence, and finally into a domain where the galaxy itself becomes the stronger force. This idea challenges the way we think about boundaries. On Earth, we expect edges, lines, fences, markers that tell us where something stops and something else begins. But in space, borders are not drawn. They are measured in gradients and changes. The edge of the solar system is not a place you can see, but a shift you can detect. That shift is scientific, but also symbolic. As Voyager 1 crossed the heliopause, it carried with it not only instruments, but a golden record, a message from humanity etched in copper and gold, designed to last 1 billion years. It includes music, sounds, greetings, and images from Earth. It was launched with the knowledge that it might never be found. And yet, it was sent, out of curiosity, out of hope, and perhaps out of a need to be known beyond our own solar family. In that way, the edge of the solar system is not just physical, it's philosophical. It's where local becomes universal, where familiar becomes unknown, and where exploration shifts from mapping what we know to wondering what lies ahead. There is a limit to what we can see, not because the universe has an edge, but because light takes time to travel. The farther something is, the older the light we receive. Eventually, there comes a point where the light hasn't had time to reach us. Not yet, not ever. That point is called the cosmic horizon. It is not a wall or a barrier, but a quiet limit defined by time and expansion. We can only see as far as the universe has existed. Light from more distant places is still on its way, and some of it, due to the rapid expansion of space, will never arrive at all. As of now, that cosmic horizon is about 46.5 billion light-years away in every direction. It defines the sphere of the observable universe, everything that has ever sent us light since the Big Bang, about 13.8 billion years ago. Beyond that, the universe continues, but remains forever out of reach, not because we lack the technology, but because the space between is stretching too fast for the light to close the gap. This concept is vast and silent. It doesn't just mark a distance. It marks the edge of knowledge, the farthest extent of what can ever be seen or measured. It reminds us that there is always more beyond our view, always more that exists, even if it never touches us. And in that idea, there is something very close to sleep. When you lie down at the end of the day, your awareness begins to recede. The mind pulls back from the noise, the effort, the shape of the day. Thoughts may drift, slowing their pace, growing softer. Some memories return, others slip away. Eventually, the conscious world becomes quiet. You approach your own horizon, not of space, but of attention. Beyond that point, you are no longer observing. The light of experience stops reaching you. And yet, your body continues. Your brain works, your cells repair. The world moves on, even as your awareness fades from it. Sleep is not a disappearance. It's a shift in perception. Just as the universe continues beyond the cosmic horizon, so does the mind beyond the edges of wakefulness. In dreams, the brain makes meaning from fragments. In deep sleep, it restores the architecture of thought. Even in stillness, there is motion. In space, the cosmic horizon is defined by light. In sleep, your personal horizon is defined by thought. One is infinite in scale, the other intimate. But both speak of limits, quiet, necessary limits that shape how we move through existence. If you are awake now, you might find yourself nearing your own horizon, not with effort, but with release. You don't have to reach for sleep. It approaches naturally, like the soft expansion of space itself. One breath, then another, and then perhaps none that you notice. The light from distant galaxies travels for billions of years to reach your eyes. The thoughts from today have only a few minutes left before they settle, and both light and thought have their place in the vast structure of experience. Astronomers sometimes speak of look-back time, the idea that seeing a galaxy 10 billion light-years away means seeing it as it was 10 billion years ago. In the same way, sleep allows us to look back, distantly, at our waking lives, and then gently turn away from them. There is no rush to cross the horizon. Just as the universe expands at its own rhythm, your mind moves at its own pace. Let the edge come when it will. Let awareness soften. Beyond the cosmic horizon is more universe. Beyond the edge of waking is rest. And just as the stars continue to shine in places you cannot see, the story continues, quietly, gently, whether you are present for every word or not. When we look into the night sky, we often see patterns, groups of stars connected by imagination into shapes, symbols, and stories. A hunter, a scorpion, a great bear. These constellations have helped humans navigate, mark time, tell myths, and make meaning out of the vastness above. But the stars themselves do not know these names. The sky is not actually divided into animals or warriors or crowns. Those are borders we made, projections of culture onto the cosmos. And yet, these projections matter. Nearly every ancient civilization created its own version of the night sky. In Greece, Orion was a hunter, strong and proud, followed by his dogs, Canis Major and Canis Minor. To the ancient Egyptians, Orion represented Osiris, god of the afterlife. In Chinese astronomy, the sky was divided into different regions, with star groups like the Azure Dragon of the East and the White Tiger of the West. The Lakota people told stories of stars as campfires of ancestors. The Aboriginal peoples of Australia saw dark shapes in the Milky Way itself, not just the bright stars. The emu in the sky, formed by the dark dust lanes of the galaxy, is one of the best known. These interpretations vary widely, yet they reflect something universal: the human need to locate ourselves in the universe. The stars became maps, calendars, and canvases for meaning. Constellations were not just decorations in the sky, they were ways to carry memory, to connect generations, to encode practical knowledge about seasons, migrations, and agriculture. Today, modern astronomy officially recognizes 88 constellations, a system formalized by the International Astronomical Union. These include both classical star groups from Greco-Roman tradition, like Leo, Taurus, and Cassiopeia, and southern sky additions like Tucana and Indus, which became visible to European explorers during the Age of Discovery. But these modern constellations are not the only way to see the sky. In fact, they are culturally specific. They divide the celestial sphere into segments for scientific convenience, but they do not replace the vast diversity of indigenous and historical star knowledge. From Polynesian wayfinding techniques to the intricate star maps of Mesopotamia, the night sky has long been a repository of both practical wisdom and sacred meaning. Importantly, constellations are not clusters of stars physically close to each other. Most are made up of stars separated by hundreds or thousands of light years. They appear close only from our vantage point. If we moved to another part of the galaxy, the shapes would dissolve, rearrange, or vanish entirely. The constellations are an illusion, useful, beautiful, but ultimately rooted in perspective. This makes them one of the most intimate borders we've ever drawn in space. Not territorial, not political, but imaginative. We've taken something endless and stitched it into patterns we can remember. And though those patterns are not fixed in the cosmos, they are fixed in memory, passed down across time and continents. There's a quiet poetry in that. In the same sky, different cultures have seen different things. A Greek shepherd and a Mayan priest, a Chinese astronomer and a Polynesian navigator, each looked at the same stars and built different maps, and none were wrong. The stars did not object. Today, we use the sky for science, measuring stellar temperatures, masses, and distances. We send telescopes beyond the atmosphere to capture faint galaxies and distant quasars. Yet the old constellations remain. They still guide our gaze, still provide a structure for naming, locating, and storytelling. In this way, the sky is both borderless and full of boundaries, human-made, symbolic, meaningful. We divide it not to control it, but to understand it. We name the stars not to claim them, but to carry them with us. So as you look upward, or simply think of the stars above, remember that the constellations are stories suspended in light, not fixed borders, but reminders of how humans have always tried to orient themselves within the infinite. Of all the things that travel through space, light may be the most revealing, the most persistent, and the most borderless. It crosses billions of light years, passes through the darkness of space without resistance, and carries information across time. It moves freely, needing no road, no permission, and no translator. In a universe divided by distance, light unites. Photons, the particles of light, are massless, yet they carry energy. They travel at the fastest speed allowed by physics, nearly 300,000 kilometers per second. That speed is not just fast, it is fundamental. It defines the limits of cause and effect, the shape of time, and the structure of space itself. When we observe the universe, we do not reach out and touch distant stars. We wait for their light to reach us. That light is the messenger. It tells us what a star is made of, how hot it burns, how far away it lies, and even how fast it is moving. Every twinkle in the sky is a note in a grand cosmic song, and the light we receive is its music. But light does not care about borders. It is not stopped by national boundaries, cultural divisions, or ideological lines. A photon emitted from a galaxy 10 billion light-years away may pass by millions of stars, cross between galaxy clusters, bend around massive objects, and finally arrive at a telescope on Earth, perhaps in Chile or Hawaii, or orbiting high above the planet aboard the Hubble Space Telescope. That photon's journey was not tracked by nations or interrupted by customs. Its path was determined only by gravity and time. The Earth it reaches may be covered in maps, but the space it crossed was open. This borderlessness is part of what makes astronomy so powerful. Anyone, anywhere on Earth, can observe the same sky. A young student with a homemade telescope in one country sees the same moon, the same planets, the same Milky Way as an observatory on the other side of the world. The equipment may differ, the interpretation may vary, but the light is the same. Even light that is invisible to human eyes carries knowledge. Infrared light reveals warm dust clouds where stars are forming. Ultraviolet light shows energetic processes in the upper atmospheres of planets and the surfaces of hot stars. X-rays come from black holes, neutron stars, and supernovae. Radio waves, the longest wavelengths, tell us about the spin of galaxies and the echoes of the Big Bang. All of these wavelengths travel together across the cosmos, interacting only with matter and fields, not with politics or ideology. They form the basis of modern astrophysics, allowing us to build detailed pictures of the universe without ever leaving our planet. And light isn't just a tool for scientists, it is a thread that connects us to the past. The starlight you see on a clear night began its journey years, centuries, or millennia ago. When you look at the star Vega, you see it as it was 25 years ago. When you gaze at the Andromeda galaxy, you are seeing light that left more than 2.5 million years ago, before modern humans existed. The light is ancient, and yet it arrives freshly, just now, meeting your eyes. There is comfort in this. In a world so often divided, where access to resources or knowledge can be unequal, the sky offers something shared. The stars do not choose who sees them. Their light falls on all surfaces equally. It is a quiet, democratic gift. And light is not always about observation. It is also how we reach outward. Our spacecraft carry radio signals, forms of light, to communicate with Earth. The Voyager probes, now in interstellar space, carry a golden record encoded with music, greetings, and images. If found, its contents could be deciphered by any being with the tools to detect light and understand patterns. In this way, light becomes not only a messenger, but a bridge across space, across species, across time. It moves without fear, without limits, without borders. In a universe filled with motion, light, and expansion, there exists one of the most dramatic exceptions to the idea of openness, a place where even light cannot escape, and where the very structure of space and time appears to fold inward. This place is called a black hole, and it is marked by one of the only true borders in all of space, the event horizon. A black hole begins when a massive star reaches the end of its life. After burning through its fuel, the star collapses under its own gravity. If the mass is great enough, no force can stop this collapse. The core compresses into an incredibly dense point, known as a singularity, a region of infinite density and zero volume, where the known laws of physics break down. Around this singularity, gravity becomes so intense that nothing, not even light, can escape. The boundary around it, the threshold beyond which return is impossible, is the event horizon. Unlike many other concepts in space, the event horizon is not symbolic. It is not imagined or theoretical. It is a mathematically defined surface. If you cross it, you will never come back. Not because of a wall or a trap, but because all paths, no matter how fast or how straight, curve inward from that point on. It is the ultimate one-way door. Yet, strangely, the event horizon has no substance. You could pass through it without feeling anything in that exact moment. No sudden jolt, no resistance. It is not a physical membrane, but a condition of the surrounding space-time. From the outside, an object falling into a black hole appears to slow down, dim, and freeze, forever approaching the horizon but never quite reaching it. From the inside, time and space become warped beyond comprehension. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners. They don't suck everything in. Their gravitational influence is only strong when you are very close. At a distance, they behave like any other massive object. A black hole with the mass of the Sun would affect Earth in exactly the same way if it replaced the Sun, except we would lose all light and heat. Black holes come in various sizes. Stellar black holes form from collapsing stars and can range from a few to dozens of solar masses. Supermassive black holes, with millions or billions of times the Sun's mass, lie at the centers of most galaxies, including our own Milky Way. It is thought that these giants play a role in galaxy formation, anchoring the gravitational structure around which stars form and rotate. Then there are intermediate black holes, whose existence is still being confirmed, and primordial black holes, hypothetical remnants from the early universe. Some theories even propose the existence of micro-black holes, which would evaporate quickly through a process known as Hawking radiation, a theoretical mechanism by which black holes slowly lose mass and energy over time. The existence of black holes challenges our understanding of reality. They force us to reconcile gravity with quantum mechanics. They raise questions about information, entropy, and whether something truly disappears beyond the event horizon. Do black holes destroy information, or is it somehow preserved on their surface, as some physicists suggest? These are not just technical debates. They are clues to a deeper theory of nature that still eludes us. In a universe largely without boundaries, the event horizon is a profound exception. It is a real edge, a limit not of territory, but of return. Once crossed, nothing comes back. And yet, even this border is paradoxical. It is invisible. It does not block. It does not reflect. It simply marks the end of freedom, of escape. That is what makes it so compelling. In a cosmos that expands without center, that blurs the line between here and there, the event horizon says, this far and no farther. It is not a border created by humans. It is a border created by reality itself. On Earth, we divide time into zones. As the planet turns, we mark the passing of hours based on the sun's position in the sky. Noon is when the sun is highest, midnight when it is lowest. These time zones are practical, human-made divisions designed to coordinate activity across a rotating globe, but they do not exist in the universe beyond Earth. In space, time flows differently, sometimes subtly, sometimes drastically. It is shaped by gravity and motion, not by geography. What we consider a second on Earth may pass more slowly or more quickly elsewhere, depending on where and how fast you are. This is not just theory. It is a physical reality, predicted by Einstein's theory of general relativity and confirmed by precise measurements. Time is not constant. It bends under the influence of gravity. It stretches with velocity. Two clocks ticking side by side on Earth may remain in sync, but if one is placed on a mountain and the other in a valley, the one in the valley, closer to Earth's gravity, will tick slightly more slowly. Now scale this up to cosmic proportions. In deep space, near massive objects like stars, neutron stars, or black holes, time slows down relative to areas with less gravity. This phenomenon, called gravitational time dilation, means that an observer close to a massive object will experience time passing more slowly compared to someone farther away. 1 second for them may be longer for someone else. Motion also alters time. According to special relativity, the faster an object moves, the slower time flows for it compared to a stationary observer. This is called time dilation due to velocity. For spacecraft traveling at a significant fraction of the speed of light, time inside the ship would pass more slowly than for people back on Earth. This isn't science fiction. The Global Positioning System, GPS, relies on satellites orbiting Earth, where both gravitational and velocity time dilation come into play. Their onboard atomic clocks must be constantly adjusted to account for these relativistic effects. Without these corrections, GPS positioning would drift by kilometers each day. Time in space truly moves differently, and we depend on that understanding for daily life. Now, consider space travel. If a mission were to take astronauts to a region of strong gravity, like near a black hole or at very high speeds, they might experience days or weeks while years passed for those back home. This idea, often called the twin paradox, has been experimentally confirmed with fast-moving particles in laboratories. Time dilation is real, it's measurable, and it reminds us that time, like space, is not uniform. The universe does not have time zones in the traditional sense, but it does have temporal landscapes. In one region, time flows gently. In another, it slows to a crawl. And across the cosmos, the age of the universe appears different depending on how far you look and how long light has taken to reach us. The light from a distant galaxy may show us a universe that is billions of years younger in appearance, simply because of the time it took that light to arrive. Even the concept of now becomes slippery on cosmic scales. There is no universal present moment across the universe. What is happening now in one part of the cosmos may already be past or still future in another, depending on the path light takes. Time is local. It is shaped by context. This challenges our everyday assumptions. We think of time as fixed, absolute, ticking steadily onward, but in the universe, time is flexible. It stretches, it curves, it responds. And so, the cosmos has no global clocks, no shared ticking metronome. Instead, it holds a vast collection of rhythms, each moving to its own tempo, each shaped by its surroundings. We still mark seconds and minutes on Earth, but when we step beyond our planet, we leave those boundaries behind. Time becomes a terrain, smooth in some places, steep in others, always shaped by the forces that bind the universe together. In a night sky full of stars and galaxies, the moon stands out as something different, something nearer, brighter, and more familiar. Unlike the distant suns that flicker from light years away, the moon is a world within reach. It has no light of its own, yet it reflects enough of the sun's glow to shape culture, science, and emotion. It is not just a celestial object, it is a mirror of memory. From the earliest human records, the moon has played a central role in how we understand time, space, and ourselves. Its phases marked the passing of days before there were calendars. The lunar cycle became a natural rhythm, guiding rituals, migrations, and agricultural decisions. In many cultures, months were defined by the moon, from the Latin mensis to the Hebrew chodesh. Even now, lunar calendars still structure sacred observances across the world, but the moon's impact is not only temporal, it is also symbolic. In mythology, it has been a goddess and a god, a trickster, a mother, a warrior. Its changing face has been read as a storybook in the sky. In some cultures, the dark side of the moon is a place of mystery. In others, the full moon is a moment of clarity, when hidden things are revealed. Its cycle of waxing and waning mirrors cycles in human life, birth and decline, hope and rest, beginning and end. Unlike the stars, the moon moves visibly each night. It rises in different places, sets at different times, and changes shape in ways that people across every continent have noticed and named. Its presence binds generations. Someone in ancient Mesopotamia could have looked up at the same full moon as you do now. It creates a thread across time. Scientifically, the moon is just as rich. It formed about 4.5 billion years ago, likely from a colossal impact between Earth and a Mars-sized object called Theia. The debris from that collision coalesced into a satellite that has orbited Earth ever since. The Moon's gravitational pull stabilizes our planet's axial tilt, which moderates Earth's climate. Without it, seasons would shift wildly, and life, as we know it, might not have developed. It also causes the tides, as its gravity pulls on Earth's oceans. This regular ebb and flow has influenced coastal life, marine ecosystems, and even human settlements. Fishermen, farmers, and navigators have relied on the Moon's influence for thousands of years. It is a force that quietly shapes the rhythm of the planet. In 1969, the Moon became the first world beyond Earth ever visited by humans. The Apollo 11 mission marked a turning point, not just in technology, but in perception. When Neil Armstrong stepped onto the lunar surface, the boundary between Earth and space was crossed not only physically, but symbolically. The Moon was no longer unreachable. It became a place with dust, shadows, and footprints. That moment was broadcast across the globe. For the first time, people of all nations watched together as someone walked on another world. The Moon became a shared destination. Its surface, once observed only from afar, was suddenly part of our collective experience. But even after the rockets returned and the missions paused, the Moon remained what it always was, a quiet companion. It does not announce itself. It simply rises, changes, and reflects. Its lack of borders is not just physical, it is emotional. The Moon belongs to no one. It is not claimed by nation or creed. It does not shine differently depending on where you stand. Its light is shared. In that way, the Moon unites. It offers a common reference in a divided world. It invites reflection not just of light, but of memory, of the things we've seen, the stories we've told, and the possibilities we continue to imagine. So when you next see the Moon, remember, it is not just a rock in the sky. It is a vessel of meaning, drifting silently above every border, carrying the quiet memory of all who have looked up before you. Sleep is often thought of as a private experience, an internal rhythm, a nightly withdrawal. But in truth, it connects deeply to the motion of our planet and the mechanics of the cosmos. Sleep is not isolated from space, it is shaped by it. The rhythm of sleep begins with circadian cycles, roughly 24-hour patterns in the body that govern alertness, hormone production, body temperature, and rest. These cycles are not arbitrary. They are tied to Earth's rotation. As the planet spins, it brings different regions into and out of sunlight. This pattern of light and dark sets the pace for life. In humans, the brain contains a cluster of about 20,000 neurons, called the suprachiasmatic nucleus, SCN, located in the hypothalamus. This cluster receives signals from the eyes about light levels. When daylight fades, the SCN signals the pineal gland to produce melatonin, a hormone that promotes sleep. When morning comes, melatonin production decreases and wakefulness returns. This entire system is calibrated to the rising and setting of the sun, an astronomical event. This link between the sky and the body is not unique to humans. Almost all life on Earth, from birds and mammals to fungi and even single-celled organisms, shows some form of circadian rhythm. These rhythms help coordinate rest, feeding, reproduction, and behavior. They are biological clocks set by celestial motion. But what happens in space, where night and day do not follow familiar patterns? On the International Space Station, ISS, astronauts orbit Earth every 90 minutes, experiencing 16 sunrises and 16 sunsets per day. To maintain healthy sleep cycles, they follow a structured schedule based on Coordinated Universal Time, UTC. and artificial lighting is adjusted to simulate a 24-hour day. Even in the absence of natural cues, the body needs a rhythm, and that rhythm is still anchored in the idea of Earth's day. As we consider future missions to the Moon or Mars, managing sleep becomes even more complex. A Martian day is about 24 hours and 39 minutes, close to Earth's, but just different enough to challenge long-term adjustment. On the Moon, a day lasts about 29.5 Earth days, which includes 2 weeks of daylight followed by 2 weeks of darkness. These patterns would require entirely new ways of managing light exposure, work-rest cycles, and psychological well-being. Sleep is not just about time, it is also about safety. In deep space, astronauts must sleep in small quarters, strapped into sleeping bags to prevent floating, protected from radiation by the walls of the spacecraft. Their brains must find rest despite noise, weightlessness, and constant activity outside. Back on Earth, the same planetary mechanics that define sleep also shape our broader cycles. Seasons, for example, are caused by the tilt of Earth's axis. They influence not only agriculture and climate, but also human behavior and mood. Some people experience seasonal affective disorder, SAD, a type of depression linked to reduced daylight during winter months. Light therapy, mimicking the sun, can help restore balance. All of this reminds us that sleep, though internal, is also external. It is not isolated from the world, but woven into it. It is not just a function of biology, but of astronomy. To sleep, we depend on the regular turning of our planet. We rely on the steady light of the sun, the consistency of day and night, and the quiet signals passed between sky and brain. When those signals are disrupted by jet lag, artificial light, or space travel, our sleep is affected. Our connection to cosmic rhythm is more fragile than it seems. And so, as you begin to drift towards sleep now, consider that you are participating in an ancient rhythm shaped by the stars. Your breath slows in time with the Earth's rotation. Your eyelids close as part of a cycle older than language. Even in the quiet of your room, you are part of planetary motion. Even in stillness, you are moving with the Earth, through space, beneath a sky that shapes every cycle. This is not coincidence. It is cosmic design. Long before telescopes, before satellites, before spacecraft and data maps, humans looked up and began to chart the stars. With no borders visible in the sky, we used patterns of light to give shape to the unknown. The cartography of the heavens, the mapping of stars, constellations, and cosmic movement became one of humanity's first sciences. These early maps were not just scientific tools, they were cultural anchors. Ancient Egyptians aligned temples with the rising of Sirius to mark the flooding of the Nile. The Maya tracked Venus to schedule war and agriculture. Polynesian navigators memorized the star paths across the Pacific to sail thousands of miles without written maps. The sky was not empty, it was a living chart. The constellations are perhaps the most familiar artifacts of this ancient cartography. Made of stars that may be nowhere near each other in space, these shapes are projections, flat drawings across a deep, three-dimensional field. Yet, they became vital for navigation and seasonal awareness. Orion, Ursa Major, Scorpius, each told a story and pointed a direction. But star maps also tell us how people thought about their place in the universe. Different cultures drew different figures in the same skies. To the Greeks, the stars were gods and heroes. To the Chinese, they were imperial symbols. To the Aboriginal Australians, they formed the dark emu, shaped not by stars, but by the dark dust between them. Even the gaps were meaningful. As time passed and tools improved, mapping the sky grew more precise. In the 2nd century CE, Ptolemy catalogued over 1,000 stars in his Almagest, defining celestial coordinates that would guide astronomers for centuries. In the Islamic Golden Age, scholars like al-Sufi revised and expanded these charts, adding measurements and correcting earlier positions. The sky became a domain of shared observation. With the invention of the telescope, the scale of cosmic cartography changed forever. Galileo revealed moons orbiting Jupiter and the phases of Venus, proof that the heavens were not static. Star catalogues multiplied. Observatories began tracking not just positions but motions, stellar drift, planetary orbits, comets streaking across paths previously thought fixed. Today, sky mapping has reached extraordinary detail. Projects like Gaia, operated by the European Space Agency, have charted the positions and motions of over 2 billion stars in the Milky Way. Each star is recorded with precision, position, velocity, temperature, brightness. It is the largest stellar map ever created, a shifting portrait of our galaxy in motion. Beyond stars, we map galaxies, nebulas, quasars, and cosmic microwave background radiation, the faint afterglow of the Big Bang. These maps help scientists understand the shape and fate of the universe. Is it flat, curved, or infinite? Where did structure form? What lies beyond the edge of the observable? We even map invisible forces. Gravitational wave detectors like LIGO and Virgo don't see light but feel ripples in space-time caused by black hole collisions and neutron star mergers. These waves come from events billions of years ago, charting cosmic violence and revealing objects we can't directly observe. This, too, is mapping, though by vibration, not vision. And then there is dark matter, the unseen scaffolding of the universe. Though we can't detect it directly, we map its presence by its gravitational pull on visible matter. Galaxies rotate too fast to be held together by visible mass alone. Their motions sketch the outlines of something hidden, something vast. We build maps not just of what is there, but of what must be. Yet in all this progress, the sky remains without borders. No nation owns a star. No telescope can claim a constellation. Even as satellites fill orbits and spacecraft cross the boundary of interstellar space, the stars themselves remain beyond territory. Our maps do not divide the sky. They illuminate it. They remind us that while we may draw lines on the ground, we cannot fence the heavens. We can only learn, chart, and understand, one light at a time. Somewhere aboard a spacecraft drifting through the vast silence of space, a human being closes their eyes and tries to sleep. Outside the window, no sun rises, no wind stirs, no sound echoes. Only stars, steady, cold, distant, float in the infinite dark. In this setting, far removed from home, sleep takes on a new meaning. To sleep among the stars is not like sleeping on Earth. On Earth, sleep is tethered to cycles of light and gravity. The pull of the planet keeps us grounded. The rise and fall of the sun helps anchor the circadian clock. But in space, those anchors are gone. Without gravity, without sunrise or sunset, the body must find new rhythms in a place where there is no day and no night. Astronauts aboard the International Space Station experience this challenge directly. They orbit Earth every 90 minutes, witnessing 16 sunrises and 16 sunsets each Earth day. To maintain healthy sleep patterns, the station's interior lighting is carefully programmed to mimic Earth's cycle. Brighter during waking hours, dimmer toward the end of the day. Yet, even with these measures, many astronauts report fragmented sleep, strange dreams, and a persistent sense of mental drift. One reason is gravity, or the lack of it. On Earth, gravity subtly signals the body when it's time to lie down. Muscles relax, fluids settle. In microgravity, these cues vanish. Astronauts float inside sleeping bags tethered to walls, ceilings, or corners of the module. There is no true down. The body must adapt to resting in a constant state of suspension. There is also noise. Despite the silence of space, the spacecraft interior hums with fans, electronics, and ventilation systems. The brain remains alert to unusual sounds, especially in a high-stakes environment. Deep sleep can be elusive when vigilance is part of survival. Still, sleep remains vital. The brain needs it to process information, consolidate memory, and regulate emotion. The immune system relies on rest. Without adequate sleep, decision-making falters, coordination declines, and mental clarity suffers. For astronauts, this can affect mission success and safety. To support them, space agencies develop sleep protocols with careful attention to melatonin production, light exposure, and sleep scheduling. Some astronauts wear visors to shield from errant light. Others use guided breathing apps or quiet music to signal the transition into rest. On longer missions, including potential voyages to Mars, sleep will become even more critical, both as a physical necessity and a psychological refuge. But sleep among the stars is not only about science, it is also about feeling. Imagine the experience of drifting off while knowing that Earth is hundreds of kilometers below, a small blue sphere wrapped in clouds. Outside, a void that stretches for billions of light years. There is no city hum, no tree rustle, no ocean wave, just the hum of instruments, the pulse of machinery, and the heartbeat in your ears. Some astronauts describe their dreams in space as vivid, strange, and untethered. With the usual rules of up and down suspended, the mind imagines differently. Landscapes melt, time slips. Memories return in unfamiliar order. The sleeping brain reaches for something constant and finds only stars. Yet, this kind of sleep is also a reminder. We carry our inner worlds with us. Even when floating through emptiness, even when far from every familiar place, the rhythms of life continue. The need to rest, to dream, to retreat into unconscious thought is universal. It persists across all boundaries. And so, as you lie down now, wherever you are not so different from that astronaut. You, too, are carried by a spinning world, circling a star, moving through space. You, too, are suspended between light and darkness, wake and sleep, memory and imagination. Let your breath slow, let your muscles soften. Sleep, like gravity, will find you, gently pulling you toward the place where thought becomes still and silence becomes soft. Even in space, where borders vanish and directions dissolve, sleep remains. It connects us to the body, the mind, and the universe itself. When we look at the night sky with the naked eye, we see stars, individual points of light scattered across the darkness. But when we zoom out, far beyond the scale of galaxies, a new structure emerges, one that is vast, delicate, and deeply connected. It is called the cosmic web, a sprawling network of galaxies, gas, and dark matter that spans the universe like threads of silk stretched across the void. The idea of the cosmic web began with questions about how matter is distributed across the cosmos. If the universe began with a relatively uniform Big Bang, why do galaxies now cluster in some regions and leave other areas empty? Why do we see filaments, clusters, and voids instead of an even spread? The answer lies in gravity and time. In the early universe, small fluctuations in density existed in the hot plasma that filled space. These were tiny, 1 part in 100,000, but gravity amplified them. Over billions of years, matter flowed towards slightly denser regions, forming strands of gas and dark matter. These strands drew in galaxies and dark halos, growing into what we now see as the filaments of the cosmic web. Galaxies are not scattered randomly. They cluster along these filaments, connected by bridges of dark matter and gas. At the junctions of filaments are superclusters, dense regions where thousands of galaxies swirl together. Between the filaments lie cosmic voids, enormous bubbles of nearly empty space that can span hundreds of millions of light years. In this way, the universe resembles a sponge or a neural network, dense intersections connected by long, thin strands with vast open spaces in between. We have mapped these structures through deep sky surveys. One of the most ambitious, the Sloan Digital Sky Survey, has measured the positions and redshifts of millions of galaxies, revealing a three-dimensional map of cosmic structure. The result is breathtaking, a web-like framework where galaxies trace invisible filaments of gravity. But the web is not just visual, it is also physical. Between galaxies, diffuse gas flows along the filaments. This intergalactic medium carries not only matter, but also energy and elements created in stars. Some of it collapses into galaxies, fueling star formation. Some is blown back out by supernovae and active galactic nuclei, cycling material through the universe like a cosmic tide. Recent observations using X-ray and ultraviolet telescopes have begun to detect these faint filaments directly. By studying how light from distant quasars is absorbed as it passes through them, astronomers can trace the location and temperature of the cosmic web's strands. What once was theory now becomes visible. Even more mysterious is the role of dark matter. Though invisible to our eyes and instruments, dark matter makes up most of the web's scaffolding. It provides the gravitational framework that shaped the universe's structure. Without it, the cosmic web as we know it would not exist. And yet, despite its size and complexity, the cosmic web has no borders. It does not end at the edge of a galaxy or pause between clusters. It is continuous, stretching across billions of light years. Even galaxies separated by vast distances remain connected through this gravitational fabric. This has led some scientists and philosophers to reflect on the universe as an integrated whole. Just as neurons in the brain form networks of information and response, galaxies may form networks of matter and evolution. Some have even wondered if the cosmos itself has an emergent logic, patterns of structure and behavior that resemble biological systems. These are speculative thoughts, not testable claims. But they remind us that in the grandest scales, separation is an illusion. The universe does not scatter itself randomly. It binds itself, strand by strand, into something larger. And though we live in one galaxy, orbiting one star, on one small planet, we are not isolated. We are connected to the filaments, the bridges, and the tides of something far beyond. The cosmic web shows us that the universe is not chaos. It is structure, it is relationship, it is pattern, repeated on unimaginable scales, and in that structure we may find not only knowledge, but meaning. In the vacuum of space, where no air carries sound and no medium bears touch, light becomes the universal messenger. It crosses vast distances, encodes the past, and reveals the structure of everything we know. The cosmos speaks in wavelengths, and to study the universe is to learn its language. Every star, galaxy, and nebula emits light, but this light is not uniform. It comes in a spectrum, a range of electromagnetic waves with different energies and frequencies. The visible spectrum, the rainbow of colors we see with our eyes, is just a narrow slice. Beyond it lie infrared, ultraviolet, radio waves, X-rays, and gamma rays. Each part of the spectrum tells a different story. Light doesn't just show us where things are, it tells us what they are made of. Every element in the universe has a unique spectral fingerprint. When atoms absorb or emit energy, they do so at specific wavelengths. By analyzing these patterns, through a method called spectroscopy, astronomers can determine the composition of stars, the temperature of galaxies, and the motion of planets. This is how we know, for example, that stars are mostly hydrogen and helium. It's how we discovered the presence of carbon dioxide on Mars, methane on Saturn's moon Titan, and water vapor in the atmospheres of distant exoplanets. We have never been to most of these places, but light has been there, and it has returned with messages we can read. One of the most important discoveries from light came from observing redshift. As galaxies move away from us due to the expansion of the universe, the light they emit is stretched, shifting toward the red end of the spectrum. This effect is similar to the way a siren sounds lower as it moves away, only in light instead of sound. The degree of redshift tells us how fast an object is receding and how far away it is. This led to a profound realization. The universe is expanding. The farther a galaxy is, the faster it appears to be moving away. This relationship, known as Hubble's law, became one of the pillars of modern cosmology. It also gave rise to the idea of a beginning, a moment when all space, time, and matter emerged from a single point, the Big Bang. Even the faintest glimmers of light hold information. The cosmic microwave background radiation, a soft glow spread throughout the universe, is the cooled remnant of the Big Bang itself. It is the oldest light we can detect, released when the universe was just 380,000 years old. This light, though incredibly faint, carries within it the imprint of the earliest structures, the seeds of galaxies and clusters that would later grow into the cosmic web. Telescopes that read different wavelengths reveal different layers of the universe. Radio telescopes peer through clouds of dust to detect the coldest, darkest regions of space. X-ray telescopes capture high-energy events like black hole collisions and supernovae. Infrared telescopes, like the James Webb Space Telescope, peer into the early universe to study the birth of galaxies and stars. Each kind of light is like a dialect, and by listening in all of them, we assemble a fuller picture. But light does not travel instantly. It moves at a finite speed, 299,792 kilometers per second. That's fast, but not infinite. It means we always see the universe as it was, not as it is. The light from the sun takes about 8 minutes to reach Earth. The light from Alpha Centauri takes over 4 years. When we observe galaxies billions of light years away, we are looking billions of years into the past. In this sense, light is time. The farther we look, the deeper into history we go. Telescopes become time machines, showing us the evolution of the universe one photon at a time. So when we gaze at the night sky, we are not seeing the present. We are reading messages from long ago, delivered faithfully, without distortion, by the most consistent courier in the universe. Light travels across space not merely to illuminate, but to inform. It bridges emptiness with knowledge, connects epochs, and unites the observer with the observed. It is the universe's first language, and we are still learning to understand it. On December 24th, 1968, a photograph was taken that would change the way humanity saw itself. From the window of the Apollo 8 spacecraft, astronaut William Anders captured an image of Earth rising above the barren horizon of the Moon. The photo, later known as Earthrise, showed a small blue sphere floating in darkness, fragile and luminous against the black. No borders, no labels, no nations, just Earth. It was the first time humans had seen their world from such a distance. Not as a map, not as a globe, but as it truly is in space, finite, radiant, and alone. This image did not show power or conquest, it showed unity. The Earth seemed delicate, even vulnerable, wrapped in a thin atmosphere and floating in a vacuum that stretched forever. The Earthrise photograph became a mirror. It reflected not just the planet, but our place within it. It became a symbol for the growing environmental movement, prompting a realization that our home is not limitless. In the years that followed, public consciousness began to shift. The first Earth Day was celebrated in 1970. Concepts like sustainability, planetary stewardship, and global responsibility gained momentum. For the first time, humans could see the Earth as a whole system, weather patterns swirling, continents stretching, oceans breathing in tides. Satellite imagery built on that perspective, offering dynamic, real-time views of environmental change. We could watch forests disappear, ice caps melt, and cities grow brighter at night. The planet became observable as an organism, alive, interconnected, and reactive. And all of this from space. But the impact of Earthrise was not only environmental, it was also psychological. Philosopher Alan Watts once said that we do not come into the world, we come out of it, like leaves from a tree. Earthrise made that statement visual. The planet was not something separate from us. It was part of us, and we were part of it. From space, borders vanish, cities dim, mountains flatten into shadows. What remains is connection. Every breath taken on Earth cycles through the same air. Every drop of water returns through rivers, clouds, and rain. The same sun warms every surface. The same night falls on every continent. Earth becomes not a place among many, but the only place. Other missions would echo this message. The Voyager 1 spacecraft, launched in 1977, carried a golden record of Earth's sounds and images, a message to any intelligence that might find it. In 1990, as it left the solar system, Voyager turned back and took one last photograph of home. From 6 billion kilometers away, Earth appeared as a pale blue dot, less than a pixel wide. As astronomer Carl Sagan reflected, "That's here, that's home, that's us." Images like Earthrise and the pale blue dot serve as reminders that space exploration is not only about reaching out, it is also about looking back. The farther we go, the more clearly we see what we have. The vacuum of space does not diminish the value of Earth, it highlights it. Our planet is not perfect. It holds conflict, suffering, and division. But from space, those divisions blur. We are a species sharing a biosphere, reliant on the same ecosystems, and vulnerable to the same planetary limits. The perspective offered by space invites humility, and with it, a sense of unity. As technology advances and more private missions prepare to carry civilians into orbit, more people will experience what astronauts call the overview effect, a cognitive shift that occurs when one sees Earth from space. Feelings of interconnectedness, wonder, and responsibility often follow. The desire to protect becomes instinctive when one sees the planet as a single, living whole. And though most of us will never leave Earth, we do not need to. The images are here, the lessons are here. The sky above reminds us every night. There are no borders on a cloud, no flags on a current, no names written on the mountains, only us, spinning quietly in the dark, held by gravity and lit by a star. What we saw in that photograph from Apollo 8 was not just Earth rising. We saw ourselves. There is a moment, late at night, when the world grows still. City lights flicker softer, voices hush, screens dim, and above it all, if the skies are clear, the stars return. For thousands of years, humans have turned upward in these quiet hours, not only to observe, but to remember. Long before borders, before nations, before history was written, we looked to the stars and found something familiar. When borders disappear, we remember the stars. We remember that they watched over our ancestors as they crossed deserts, sailed oceans, and built the first villages. We remember that constellations guided planting and harvest, migration and myth. Before we drew lines on maps, we drew shapes in the sky, and through those shapes we learned to measure time, to tell stories, and to imagine something larger than ourselves. In the deep time of human history, sleep and starlight were companions. Without electric light, night was vast and dark. The stars were not just distant fires, they were a kind of company, constant, dependable, slow-moving across the sky. People slept under them, prayed to them, told their children stories about them. The boundary between night and dream was porous. Even now, in the age of satellites and space stations, that ancient connection persists. The stars have not changed. We have. But when we allow ourselves a moment to lie still, to look up, we can feel that same quiet unfolding. The stars ask nothing. They impose no borders. They simply shine. Astronomers have now charted the positions of billions of stars. We know their distances, temperatures, life cycles. We understand how nuclear fusion burns hydrogen into helium, how supernovae scatter heavier elements into the cosmos, how gravity sculpts galaxies from clouds. And yet, with all this knowledge, the stars retain their wonder. They are not diminished by science. If anything, they are deepened by it. Because to know how stars are born is to understand the past of our universe. To know how they die is to glimpse its future. To know what they are made of is to realize, so are we. The carbon in your cells, the iron in your blood, the calcium in your bones. These came from ancient stars that exploded long before Earth existed. We are not just looking at the stars, we are made of them. And in that truth, borders dissolve completely. The idea of us and them loses meaning when traced back far enough. Before language, before land, before law, there was stardust, and stardust does not recognize borders. This is what space reveals, not just distance or data, but perspective. It reminds us how little separates one person from another, how small our divisions look from orbit, how fragile our planet appears in the vastness of everything, and how sleep, even among the stars, is still a part of life. Tonight, as you settle into stillness, know that you are part of something vast, not just in time, but in structure. You are drifting gently on a spinning planet, wrapped in a thin shell of air, held by gravity and warmed by a star. The thoughts you carry, the dreams you form, are not separate from the universe, they are shaped by it. Let your breathing slow, let your mind soften, let the imagined lines of nations and names melt into the fabric of the night. The stars do not ask for boundaries, they offer only presence. And if sleep has not yet come, that is completely fine. In these moments of rest, you are learning the language of stillness. You are floating, like a satellite in orbit, weightless and quiet, among memories written in light. For all the science we've learned, for all the maps we've drawn, one truth remains. Space has no borders, only motion, only light, only the enduring rhythm of stars and the gentle pull of sleep. We, from Sleepy Stories, wish you a good night.